Welcome to The Explainer. Today, we are diving into a really cool idea that lets us shrink massive AI models. I mean, really shrink them down. But the secret isn't about getting more powerful computers. Nope. It's about changing the very shape of the universe the AI lives in. All right, so let's get right into it. Why is something like an AI search so ridiculously expensive? Every time you search for something, talk to a chatbot, there is a huge cost happening behind the scenes. And it's not just the electricity bill, it's the massive, super expensive memory that's needed to make it all work. And to put a number on that, just storing 1 billion documents for a smart semantic search can take up 3 terabytes of RAM. We're talking thousands of dollars every single month. That kind of cost puts this amazing technology way out of reach for pretty much everyone except, the huge tech companies. But what if the problem isn't that we need bigger computers? What if the real issue is that we've been using the wrong kind of math this whole time? What if we're trying to cram our data, which is all complex and branching, into the wrong shaped box? This brings us to what you could call AI's flat Earth problem. Seriously, we're trying to map the incredibly rich, branching world of human language onto a totally flat, limited digital space. And well, you can probably guess that's causing some major issues. So here's the fundamental mismatch. Think about it. Information, especially language, is hierarchical. It's like a tree, right? It branches out from a trunk to limbs to tiny leaves. But our standard digital models, they use something called Euclidean space, which is basically a flat sheet of paper. Okay, here's a great way to picture this. Think about your own family tree. You've got 2 parents, 4 grandparents, 8 great-grandparents. The number just explodes. It grows exponentially. Now imagine trying to lay out photos of all of them on your living room floor. You would run out of room in like 2 seconds because your floor space is flat and limited, but your family tree just keeps expanding outward. Well, in the world of AI, this exact problem has a name: over-squashing. Just like you'd have to stack photos on top of each other, the AI's flat world forces it to cram different ideas together. And that's where the trouble starts. You get confusion, you lose context, and you get what we all call AI hallucinations. The system literally runs out of room to keep things straight. But what if we could just change the shape of the universe where all this data lives? What if we could build a container that actually grows just as fast as the information we put inside it? Well, this is where a really fascinating bit of math called hyperbolic geometry comes into play. And here is the solution. On the left, you see our old friend, the flat Euclidean space. But on the right, that's hyperbolic space. Now, I want you to forget about a flat sheet of paper. Instead, I want you to think about something more like a cabbage leaf, or maybe a piece of coral. It's a space that's curved everywhere, all the time. So why a cabbage leaf? It's a weird analogy, I know, but look at how its edges get all frilly and ruffled. That's because the surface area on the edge grows way, way faster than the area in the center. It has what's called excess area. And guess what? Hyperbolic space does the exact same thing. It creates a universe that expands exponentially at the edges, giving you more and more room the further out you go. And this is the magic trick. It means you can finally map those complex tree-like structures, like our language, without ever running out of room. Ideas that are really different from each other can be placed way out near the edge of this space, where there's basically infinite room to keep them separate. No more over-squashing. Problem solved. Okay, so this all sounds great in theory, but you're probably asking, how do we actually do this? How do we move our data from its flat world into this new curvy universe? Well, researchers came up with this really elegant method called contrastive geometric transfer, or CGT for short. And the process is actually surprisingly straightforward. First, you take a huge piece of data, what we call a vector, from a normal AI model. Think of it like a really long, super detailed street address. Then, a small neural network acts like a summarizer. It just finds the absolute core essence of that address. And finally, a special mathematical function projects that core meaning perfectly onto our new curved map. This exponential map thing, that's the real key to the whole process. It's the mathematical translator that lets you go from the flat world to the curved one. It's kind of like a pilot's autopilot. It makes sure that when you go from looking at a flat paper map to the actual curved globe, you land in the exact right spot, keeping all the important relationships intact. So how does the model get so good at this translation? Well, it learns by contrast. During training, you show it pairs of sentences, And it learns to pull the similar ideas closer together in this new curved space, while at the same time it's actively pushing the different ideas far, far apart. It literally learns to preserve the meaning of the original data. But of course, the real test is in the results. And honestly, the outcomes of this little geometric trick are, well, they're nothing short of astounding. This is where all that cool theory becomes a mind-blowing reality. So what's this number? 97.4%. That is the percentage of the original model's quality that was kept after being compressed into this new space. That's an almost tiny, negligible loss for a truly colossal gain in efficiency. It's amazing. Let's just look at a direct comparison here. The top model, MPNet, uses 768 dimensions, that's its size, to get a quality score of 0.834. Okay, now look at the new CGT model. It uses just 32 dimensions and gets a score of 0.812. Let that sink in. That is a 24 times reduction in size with less than a 3% drop in quality. It is almost unbelievable. So why does all this matter? I mean, this isn't just some clever math trick. This could fundamentally change who gets to use powerful AI. We're talking about AI search that can run entirely offline, right on your phone. It means startups can suddenly afford to build search tools that can compete with the biggest companies in the world. This is the democratization of AI on a massive scale. So, in the end, the solution to AI's expensive flat Earth problem wasn't more brute force. It wasn't bigger computers. It was just elegance. It was about finding the right home for our data. As this quote says, the holy grail of vector search wasn't a bigger model. It was a smaller space, curved just right. And that really makes you wonder, doesn't it? What other huge problems are we trying to solve with brute force when all we really need is a change in geometry?